way through. Thank you for coming. My name is Michael McCarthy. I'm a professor at the University of California, Irvine. And I'm here to talk to you about synthesis of planar 6-bar and 8-bar linkages. Now, it's a fair question, or at least the fair question is this. 6-bar and 8-bar linkages? Are you kidding me? All right. So, first of all, let me give you a little bit of understanding of what I would like you to get out of my presentation today. Sort of at the heart of what we're working on, or at least this the series of presentations are that you have in this particular summer school, really is on the computer-aided invention world. So the idea that the computer should be able to help us as designers find new solutions to mechanical systems. Now that's only about a third of what we think Kinematics is addressing and is focused on. When we had our 21st century workshop on Kinematics, we really had three broad areas. One was mechanisms in robotics, the other mechanisms in robotics, the other was compliant mechanisms and cable-driven systems, and then the third was sort of protein kinematics and microsystems. So there are these broad areas, and what we're focusing on here is, I would say, mostly in the mechanisms and robotics side, and there's all this theory that we're trying to pull together to present to you today. That theory applies in the context of kinematics, in compliant mechanisms, and in the context of protein kinematics and microsystems. It's just that those other areas have even more specialized knowledge, stress analysis, topology optimization for, and we're not going to be covering that. We're really sort of focusing on the specific issues of how you formulate a design theory for machines. And now it may not look like it, but that's sort of where all of this theory comes from. And when we're talking about, I'm talking about planar linkages, and this is my apology right at the start. Most of my students, Jeff absolutely knows this. I would never let any of my PhD students work on planar mechanisms. In fact, I regularly get ribbed by, Pierre and Drew and all of this walk up to me, oh my gosh, have you seen another planar mechanism presentation by Professor McCarthy? When is he ever going to get the word? Do you know what I mean? And I deserve it. I absolutely deserve it. They were, the plane, planar geometry is so rich, it sucks you in, and at least during the 20 plus years that we were coming to this conference, dealing with planar mechanisms, it seemed like every day there was some new kind of interesting feature we discovered about a polar-bar linkage. And I told them, no, you can't do that. We have to work in space. Well, space is incredibly tough. Just getting the mathematical formulations and the theoretical formulations to make sense is incredibly tough. What I'm here to talk to you about now is that, to a certain extent, using these theories that Anurag and Jeff have been talking to you about, they actually provide a mathematical connection between what we need in terms of spatial theory in order to manage things like robotics, inverse kinematics, path planning, protein kinematics, and all of that kind of stuff. It's got a nice blend that now moves down into spherical mechanisms and into planar mechanisms. So this is my apology, and I'm going to say it. When you see Pierre, you can tell him, well, he tried to explain it, but I still don't buy it. But anyway, and that is that the theory that we're using in planar mechanisms now can generalize to the sphere and into space, and that it makes the plane a good place to tackle really tough problems, tougher than you'd be able to handle in space. Not as tough as you would have in space, but gives you a place to practice challenging problems with the hopes that you can then move it up to space. And that's kind of that's what we're doing here. So we're really looking at large numbers of links. I'm trying to get to large numbers of links. In order to get to a large number of links, you got to go from 4 to 6. and now recently we've gone from 6 to 8, and I'd like you to start to see what the challenges are if we're going to go to, you know, 30 and 100 and maybe 200. You know, I mean, a protein molecule has 10,000, you know, components that you can think of as links. I mean, it's just, so if we're going to start doing those kinds of problems, we got to get out of, we got to get moving, I guess is the basic idea. So the notion of a you know, two loop link, you get it basically every time you add 2 links, you get a loop roughly. That's sort of the way it works. The 6-bar Watt mechanism can be considered, you know, the invention that made the Industrial Revolution possible, right? I mean, do you believe that I'm too extreme in that? Watt himself says that the parallel motion generator, which is a 6-bar linkage that allowed this vertical movement, was his greatest invention. From the guy who not only made the steam engine possible, he also manufactured it efficiently and marketed it efficiently and got it into all kinds of applications, not just to getting water out of mines and so. Anyway, the 6-bar linkage shows up. I mean, these linkages are common. There's even 8-bar linkages that show up in walking machines. They're designed by, because they're in the plane, they're designed by artists. They sort of sit there and they sort of draw them, they sketch it out, they imagine how it's going to work, they make a little model, and they do a great job. This guy, Theodore Jensen, I mean, he makes these gigantic walking machines that are just beautiful. They don't need me, okay, and I'm not claiming that they do. I need them so that I have some inspiration and see, and they give me a test case that I can measure myself against. This is what we're up against. We get this combinatorial explosion as soon as we start adding links. You know, the 4-bar linkage, which, you know, okay, I had to come to conferences year in and year out and hear people complain, well, are you guys ever going to quit studying the 4-bar linkage? Look, I get it, okay, but converting what were incredibly rich graphical synthesis techniques into computer algorithms that would do something similar was not an easy task, and it took a lot of people a lot of time to figure out how to turn those graphical calculations into polynomial equations that we could formulate and solve and present graphically to the designer. And that's what we spent most of the 80s and 90s doing. Those days are gone. We don't have to worry about that anymore. I mean, we've got incredible computing resources that I mean, it's like silly to even mention it, but you know the kinds of computers that we used to work on, which were, you know, 10 times, 100 times better than what our advisors worked on, just makes this really an opportunity. It gives us no excuse to not be exploring these kinds of opportunities, the kinds of things that we're seeing. Anyway, here we're at 8-bar linkage, 10-bar linkage. See, every time we add 2 bars, we get another loop. We get more and more complicated ways that links can be assembled. We'll have 4 dyads, 6 triads, but you can also get all the way up to quadriads in these 10 bars. These are links that have lots of joints connected to them. You've got 230. Of course, this is an old result. This is Erskine Crossley's famous result, and he of course almost single-handedly founded the International Organization of Mechanisms in Machine Theory. Trying to turn this result into something practical so that we can actually design something is sort of where me and my students are at the moment. Okay, we are, I mean, the biggest result, this is what blows my mind, you just get up to 16 joints and you've got 19 million topologies. And that's not even, I mean, that's not even choosing which link is going to be the ground link and which link is going to be the input link. I'm going to show you some of our results on that. So that makes you think, you know, the fact that we only have 21 proteins, or what is it? I mean, it's like 29 proteins that make up the entire life on Earth, when you've got 10,000 of these joints that could be combined in so many different ways. Makes, you know, at some point we do have to start trimming it down and seeing what we can do with, without exploring everything. There's just not enough computation time. When we talk about a topology, we really don't distinguish which loop is ground, which link is ground. And if you choose which link is ground, you get sort of the 5 mechanisms. one of the things it matters to us which is the input link. So this input link is different from that input link. So when you start talking about it, you actually start getting more. You get like, and that turns out to be an issue that just grows in its challenge. Here's what happens with the 8 bars. We know we've got 16 8-bar linkages. You've got to start turning this into some sort of scheme where you can evaluate it. So you turn it into a graph, and then you use an adjacency graph. And then what we did is we start deciding which link is the ground link and which link is the input link. And you wind up coming up for at least 8 bars. You have 156 of these. And this isn't any link as the input. This is only one of the grounded links as the input. For example, if you're like someone like Andrew Murray, who likes to consider the problem of the input link maybe at one of the other links because there might be some sort of actuator on it, that number would go up. This is only if it's the grounded link. So this is what we're dealing with. Now, one way to look at this is that this is a combinatorial explosion. This is going to just use up all my computing power. Well, the other side is this is a huge opportunity. If you think about everything that we can do with a 4-bar linkage, and it's, I don't care which side you put to ground, it looks the same. It's a quadrilateral. But it makes a big difference if one is small or one is large. It's a drag link if the ground is small. It's a double rocker if the input is small. So we haven't even gotten to that to try to think about these devices. But what we can do is we can apply traditional, old school synthesis theory and design large numbers of these linkages and see if they're useful. That works, that's efficient, it's not hard to do, and it's actually been fun, and I'm hoping that you'll see some of that in what I have to present to you today. Okay, let me just point out, this is just to give you a taste of what we're going to see, because I'm going to push you through sort of a desert. I'm going to ask you to struggle, or maybe let's put it this way, it's going to be a steep climb. I'm going to give you this real steep climb before I then we'll start gliding down a little bit, and then we'll have a little bit of a hump, and then we'll glide out to you. So this is just meant to get your energy up and help you think about what the kind of opportunities are that we might have. This is a traditional, what I'm showing here, this is GeoGebra. I don't know if you're familiar with GeoGebra. This is a graphical implementation of a very old traditional technique for taking a 4-bar linkage, adding 2 links, so that the link that you add just makes pure rectilinear motion. It's not rectilinear in a straight line, but it doesn't rotate. Very nice tool, very effective. Takes a lot of geometric insight to see that, to pick that out. But it's really nice. As a designer, you can sort of see how useful it is. This is an old result. This is Kemp. You can get this. This book is now available by looking at the geometry, sort of the mathematics of parallelograms and kite linkages and rhombus, and how all the points move when these things move. He was able to, he and his colleagues, this is in the 1880s, that book's available, this is where we got these pictures. He and his colleagues were able to identify that if you assemble these links in this particular way, you get pure rectilinear motion, pure straight line motion. Not just straight line motion, but straight line motion where there's no rotation. And in fact, if you assemble it in a different way, you get, same sort of thing. This one goes this way, this one, this link, instead of going in and out this way, this now goes in and out this way. 10-bar linkage, 10-bar linkage. Okay, no problem. Out of some of the synthesis theory we've been working on recently, we wound up getting this 8-bar linkage that does rectilinear motion. Doesn't do it as accurately as this. It's about one part in 1,000 offset in terms of its motion. But once you do something like this, I showed this to my colleague. He says, that would really be good. If we would probably use this, or could use something like this as a suspension in a gyroscope, in a MEMS gyroscope. but we need more breadth. I go, what do you mean need more breadth? Well, you know, we would want to chain a couple of them together. Oh, I said, no problem, I can chain them together. So we chained them together. So we did this. So this is, you know, you have to find the right spot, but you sort of connected two of them together. And he says, no, you misunderstood. We would want to stack them up so you would actually amplify their motion. I said, no problem. Stack them up, we'll amplify the motion. So that's what this one is. And now I've gone from an 8 bar to a 16 bar to a 32 bar. And what I'm really showing this to you because whenever I've done synthesis, whenever I've done any kind of synthesis tool, and I've done it for many years, and I take it into a classroom to a bunch of students and I say, all right, you have to choose the task positions. In other words, I've created the tool, you have to tell me what you want that tool to do and we'll make it work. And they go, well, what do you mean, Professor McCarthy? They said, well, you have to tell me, you know, so it's an opportunity, a teachable moment. Well, when we talk about position, we're talking about coordinate frames, we're measuring positions, coordinate frames relative to the ground. We want you to tell me how that, I want you to tell me how that coordinate frame is going to move. And I invariably do it exactly like that. You know, I'd say, it's here, it's here, it's here, it's here. So in my mind, they're kind of making some sort of arc with the origin of the reference frame and at the coordinated rotation of the frame. Invariably, they go, no problem, I've got positions for you. What they do is they put the origin on a circle and the x-axis tangent to that circle. And if they don't do that, then what they do is they put the origin on a straight line and the x-axis along that straight line. And of course, neither of those two cases can my algorithm solve. They always get singular, so then they can't solve the equation. So I'm already discredited as soon as I walk into this thing. So one of the first things I did with my own students when we were working on this theory, I said, whatever we do, let's make it move on a straight line. Well, what's remarkable is if it moves on a straight line, then you can sort of stack these things up. Oh, thanks. I didn't realize. All of a sudden I'm choking up there. What you can do is you can stack them up. You can add them. There's sort of this symmetry feature. So that's what you see here. And that's why we're all easy. We can take this 8-bar linkage and get it to be a 32-bar linkage without even thinking. Okay. That's my warm-up. That's my, in some sense, promise, because we're now going to be entering, we're going to have a little bit of a steep climb. But you've had plenty of warm-up already. I mean, you have had plenty of introduction. You guys are really tough. Anurag's presentation on Clifford algebras and Jeff's discussion of planar quaternions, which is essentially what I'm going to be telling you here now. But I'm going to tell it, I would like to tell it to you from a slightly different perspective and as my justification as to why it's important. This is something you should be familiar with, an open chain spatial mechanism, and modeling it using the Denefit-Hartenberg convention. Specify an axis, you specify a line for every joint axis, you connect every set of joint axis lines with a common normal. You can introduce a set of reference frames that allow you to write the kinematics equations. So any spatial serial chain we can write a set of kinematics equations for. That should be something that all of us understand and know. There's plenty of controversy, at least even at my university, where people say, well, the Denefit-Hartenberg form is so old, it's kind of ambiguous in certain situations, you should be using the product of exponentials form. Okay, I don't know if you guys have heard that. It turns out, you know, me, that's like Brer Rabbit. They say, oh, please don't throw me into that briar patch. Product of exponentials forms turns out to be the matrix form of Clifford algebras and, in fact, of dual quaternions. So it actually takes a little bit of work to get from the Denefit-Hartenberg mathematical formulation to quaternions. That work happens to be going through the product of exponentials. So there is no, do not fall for anyone who pretends there's any kind of controversy in terms of the formulation of kinematics equations of the robot. There's not. All right, we all use the same basic form. And they're all there to model a serial chain. And that modeling of the serial chain turns out to have very practical benefit, not just for multi-body dynamics or for inverse kinematics or analysis. It has practical benefits for design. Okay, it looks like a horrible problem, right? Suppose instead of, and these are the joint parameters, this is how much it rotates around any particular joint. Normally we think of the link parameters as given to us. Thank goodness. All right, then we've got the joint parameters, link parameters, joint parameters. But if you wanted to, and in fact we have done this, you can specify what we call the task positions, or you might call it the workspace, and then solve these equations not only for the joint angles, but for the link dimensions. This is conceptually, it's clean. You can identify how many task positions you need to solve all of the unknowns. And it turns out to be a very straightforward thing to do. And this is, in fact, if you now think this through and you apply it, this turns out to be exactly the way we do planar synthesis. It takes a while to see that, and I'm going to try to walk you through it. Now, how you get from the Denevit-Hartenberg equations to product of exponentials and dual quaternions is a very simple trick. You choose a reference position, you choose a reference configuration of the arm, and then you calculate relative movements. So you just take your kinematics equations, you multiply by the inverse that define, you just figure out whatever the joint angles that define your reference position. They could be 0, but they could be anything. Okay. And you multiply by the inverse, you group it, and what you get is a sequence of relative transformations that these matrices can all be turned into the standard product of exponentials form. All right. And what you get, you wind up getting this Fluker coordinates that define each of the screw axes. They actually will have, you can generalize them to screws if you want. Nobody does this. No one defines a joint angle, a joint axis, as both a combined rotation and translation. But you certainly can do it. And what that does is that allows the same formalism to handle straight line movement as pure rotation. From that, from these parameters, you construct this, and what you find is that those matrices that we calculated on the previous slide are nothing more than the exponentials of this twist matrix. That means that the relative transformation matrix that I just showed you is exactly this product of exponentials formula. The connection between the traditional Denevit-Hartenberg form and the whatever you want to call it, the product of exponentials form, is simply this notion of relative displacement. It turns out that that product of exponentials matrix goes right into a dual quaternion. So, I mean, it's not sort of related. With just minor adjustments of notation, you get dual quaternions, where each of these quaternions is the cosine of the relative rotation angle, sine of the relative rotation angle, times the screw axis. So this is your e to the theta 1 s1. This is your e to the theta 2 s2. And what that tells you is that the dual quaternion is defined by relative transformations, not directly by the Denevit-Hartenberg formula. All right. We've done it. We've used this. We've worked it. We've designed SS platforms using this, which is a real nice problem. Partly the reason why I show you this is that SS platform is a 1 degree of freedom mechanism. When you trace a trajectory, when you examine a trajectory, I don't know if you can see them, but there's 7 task positions on here. They're sort of on here. You can sort of see them. This is the trajectory of the origin of those task positions. I mean, don't get me wrong, it's spaghetti. It's incredibly complicated. The fact that it's deterministic at all is kind of mind-blowing. Okay? And the fact that we can design this, and we can analyze it, and we can track it. I mean, in this particular design, you see there's none of them that worked. Not a one of these linkages we designed worked, because the dark line sort of shows you when you're actually passing through. So you see some of these task positions are on one branch, some of the other task positions on another branch. Here it goes from light to dark. That means this is a singularity. The system sort of locked up in some way. Sorting this out is incredibly tough, but this turns out to be what computers do really well. Turn it loose. Let the computer figure it out. All right. We actually applied this. What this is that what you see here is a 5SS chain that has been designed for the front wheels so that when you turn, the idea when you turn, that front right wheel, because of the roll of the car, gets a lot of load. So if you sort of move that wheel out a little bit, you actually get some more stability in turning. Not only that, since you know that the car is going to roll in that direction, if you lift up the inside wheel, you basically allow the weight of the car to sort of work against the roll. So they're just simple concepts. See, but now you have to combine that with steering. So you're going to actually have to turn the wheel. Not only that, you want to maintain some sort of Ackermann steering so as you go around the inside, you don't turn as much as the outside turns. And you want that to accommodate. And it turns out all of those requirements are relatively simple to impose on a 5S suspension design, steering system design. But one solution isn't enough. You've got to now let the computer grind through, and you've got to give some sort of tolerances. If it doesn't find a solution, it's got to be able to search around and then check and finds a solution. And that process turns out to be remarkable in what you can find. Part of why I'm showing you that is because that's probably the last of the spatial mechanisms you're going to see in my talk. Because what we're doing is we're now trying to take that general theory. By staying within the context of that theory, let's look at what we can do in the plane. And part of what I'm going to pitch here to you is a realization that much of the planar theory we have actually is a specialization of all of this stuff. Clifford algebras, the quaternions and planar quaternions are not that strange. We're using them in funny ways that we don't quite recognize. And that if you recognize that, you now have a pathway up towards generalizing them towards solving tough problems in space. So here's the same problem. All this is a robot where I treat it as a spatial robot, but in each case that the axis now comes out of the plane vertically. Okay, so each of the joint axes are sort of in the z direction. When you do that, the screw matrix specializes to this simple form. Turns out there's nothing in the z direction, the twist matrix. When you take the exponential of it, you get something like this, which is what you would hope. It's a rotation matrix. The z-axis and the w-axis sort of don't move. That represents the translation associated with it. And it's not uncommon. You'll wind up seeing a matrix that looks like this. So this is the product of exponentials form of the planar robot. It turns out it has a form that's somewhat familiar. Any of you who've been involved or sort of studied with Art Erdmann and worked with his standard form equations, some of this will look familiar to you. This is the standard rotation. This is the translation term written in terms of the pole. You wind up seeing the pole show up in this context because the pole is really there. The pole is your bearing. Okay, so it's got physical meaning. The actual translation vector doesn't quite have the same meaning as the pole of the displacement. Once you have this, you can now write your kinematics equations, which are exactly the robotics kinematics equation. And they separate into two forms. You get the rotation part, you get the translation part. This is, you can find this, exactly this equation. You can find exactly these equations as Sander and Erdmann's standard form equations for the synthesis of mechanisms. Okay. So it may be a little bit of a stretch But what I'm trying to tell you is that the that we've been using, in essence, the Clifford algebra formalism is a large part of our synthesis theory for our mechanisms for a long time. Okay. One of the big complaints, one of the big struggles was how do you take that and generalize it to the sphere so that I can take all the nice theory that we know works so well on the plane, how do we now wrap it on the sphere, which we can, our intuition says should be much easier than you look. It turns out this provides a good guide to that. Next problem is how do I now move that into space, and it turns out again this provides a good guide. Okay, so that is my pitch, except I wanted to add this little twist. This is, we have this notion of the Clifford algebra formulation. So I'm just going to give you this, I'm going to just talk you through it. Someone asked me earlier, what is the advantage of the Clifford algebra formulation? The Clifford algebra theory really is something remarkably simple. At the base of it, it's just two ideas, okay? One is that you start with a vector space, right? You start with a vector space. You now allow any of the elements of that vector space to multiply with each other, okay? And then you add this one thing. Well, I guess that's three. Well, no, it's a vector space where you include multiplication. The second thing is you simply allow multiplication to be defined by this Clifford algebra product. That's all it is. It's just that Clifford algebra product. And that Clifford algebra product says that if you multiply x times y and add it to y times x, it's got to be equal to some constant times the dot product between those two vectors, between x and y. And that dot product it directly links geometry to algebra. There's nowhere else in the formalism of algebraic systems where you see the geometry, which measures distance and angles, tied so tightly to the algebra in space, literally whether the multiplication operation commutes or not. And on top of that, that dot product can be general. It can be any dot product. It can be and in fact, it can be a degenerate dot product, which turns out to work perfectly when you're working with projective space. When you want to have that extra homogeneous parameter, you know, you want to have x, y, and 1, so that your displacement equations are a linear transformation. I mean, it just works better on a computer that way. Having to keep that displacement term, that translation term separate is just really a pain. All you have to do is have your dot product make that third component 0. Once you've done that, here it is right here. So here's my dot product. All I do, and it's got 3 components. It's a homogeneous parameter. I'm talking about the projected plane through z equal 1. All it does is just get rid of the last one. It's just got 0. Okay, so and that turns out to be all you need. You now turn the crank using the definition of that product operation, and it all comes out. You get what are traditionally known as planar quaternions. You get regular quaternions that way. You get dual quaternions that way. In fact, you get sort of all of the interesting mathematical formalisms that our physicists are using this day in that way. Okay. All right. Now this part is somewhat new. This is just I think you sort of saw this. We can represent a planar quaternion as a complex number in an interesting way. What is not so well known is when you can multiply. And it doesn't take much to connect the dots, but when you can multiply, then you can compute an exponential. An exponential only depends on the ability to multiply, so you can compute this thing. When you compute this thing, you wind up seeing you wind up getting the planar version in the Clifford algebra formalism of those matrix exponentials. When you do the sort of equivalent of the matrix exponentials within the Clifford algebra, you get all of those. You get sort of the standard form equations. You get everything else. And you actually get, it's not as pretty, I'll grant you that. We get these equations like this. this is more meant for your notes. This isn't meant for you to recognize while it's on the screen. This is meant for you to look at home at some point. But what you can do is you can get nice equations like this. This is the matrix exponential form of the kinematics equations of this chain. And so there it is. You rotate theta over 2 about the first pivot, then you rotate theta 1 over 2 by about the second pivot, and once you've done that, you get the rotation by phi around the pole. All of these things are written in terms of the poles, just like in space they're written around relative to the screw axis. These things are very tied. The mathematical formalism is tied directly to the geometry. Okay. Now this is our choice. It wasn't necessarily the best choice, so this is all I've got. And we haven't actually been looking at this in a while. You take this, you write it in 2 pieces. We write it with the sine term here just because we wanted to get things into a particular format. So you get the rotation term here, you get the translation term here. What you see is that we don't have the translation term written explicitly, we do it in terms of the pole. This is what we use for synthesis. And this is exactly the representation of what I showed you on the first page with all of those kinematics equations equated to various task positions. This is what we do. We want to design this thing. We say, okay, where do we want the robot to reach? We specify all of the places we want it to reach. We now write the kinematics equations with this moving pivot unknown, the fixed pivot unknown, all of the joint angles unknown. We write them all out, and we solve the equations. And it turns out to be surprisingly simple because what you wind up doing is you wind up getting algebraic equations that we already know. You wind up getting the algebraic equation of a circle. Why? Because that moving pivot has to travel around a circle, around the fixed pivot. Duh. Okay. It works. It does, though, help you formulate the problem for not just the 2R chain, but the 3R, 4R chain. And you get a nice set of mathematical equations you can solve for that. This should bring me to the end of our hike up. Okay, we have used it to design all of these chains. Okay, and it was a really rich and rewarding study. What we're trying to do now is say, okay, we got that it can work with serial chains, and we know that we can do it when we combine 2 chains together. Let's just go after complicated systems. Okay, so what we're going to, okay, this is the basic question. Is any of this useful? Well, what do we mean by the term useful? Well, does it do something? Does it give me something that somebody can use that they couldn't get any other way? What that means is that, they probably could get it just by trial and error, particularly with planar mechanisms. So if they kind of draw it out, they can just test it. So what we really want to do is be able to have a system where we can generate lots of solutions, analyze lots of solutions, and let the designer look at the solutions and say, oh, hey, I like that better than I like that. And that's the kind of thing that we've been working towards. Okay, so what we've done is this. We sort of took the position. This is again, but this turns out to be, when you come at it this way, you really begin to discover that the weak link in the entire thing is what I was telling you, which is the choice of the task positions. Sure, once you give me the task positions, I now have the information I need to solve all of these problems, but who knows what they want as a task position? Nobody. Nobody even thinks of formulating a problem in terms of locating a bunch of task positions. And so that's turned out to be a very interesting outcome of all of this process. And that's also what makes what Jeff is talking about so interesting, because he seems to have a way to connect the task positions to general forms of the linkage that we might be able to take advantage of. Anyway, the way we do it is kind of the, basically straightforward approach. Because it seems the world, it seems your designer, seems everybody is relatively good at thinking in terms of robotic systems. In fact, they all do it, or at least I do it. here it is. Here's my robot holding my task position. Well, what do you want your task to do? I don't know. I think I want it to go, I think I kind of want it to do this. Well, I can look at my robot, or my arm that's attached to it. That sets the boundary of the workspace. It sets the range of motion I want. It sort of sets how, the relative angles, do I want it to twist around or not? So that's what we did. We said, okay, when we specify the task position, let's not just specify the task position. Let's also specify a device that sort of does the job. So give me a robot arm that would do the job. You might say, in fact, some people will say, well, why don't you stop there? You got a robot that does the job. Well, okay, a robot that does the job for $5,000, and then you're going to just hook it up, run it. You have this beautiful, expensive computer that you've used to program it, and then you're just going to use this thing cycling itself around. That's a lot of overhead, for the job you're talking about. Sure, that might be right, and if that's right, because you're going to reprogram it and use it in another place in another month or two, that's fine. But what about just taking a minute to see if we could just adjust the dimensions, bolt it together and attach a motor that just turns around and get the whole thing done for maybe same amount, I don't know, same amount, $1,000, I don't know, $100, who knows? I can't say I've done the economics on this very seriously. But it does seem that going to the trouble of programming a complicated electronic system as opposed to drilling holes and mounting good bearings and whatever it is you have to do, or at least comparable, and that the reliability of one may be at least as good or maybe better than the other. So that's the exploration, that's the goal. Okay. What's the process now? Oh, we just calculate our constraints. We calculate a constraint on the first link, then we calculate a constraint on the second link. Turns out it's really simple. It's exactly the same synthesis equations, and we're done. That's turned out. I'm going to walk you through some sort of just interesting things. Once you've decided to do that, okay, I'm going to take a serial chain and I'm going to constrain it. Well, I can constrain the end effector to the first link, and then I can also constrain the end effector to the ground link. Oh, wait, I can also go the ground link to the second link and the ground link to the end effector. Oh, wait, I can also do, you know what I mean? You start realizing I've got sort of alternatives. And not only that, if I connect the ground link to the second link, I could also connect the end effector to that link. And depending on, so I wind up going through these combinatorics and I wind up getting, all these different mechanisms. So we've encoded this in some software that you can see on the internet. And I actually teach it to my students. And I just wanted to give you something to look at. Now this is a problem that my daughter came up with. My kids are always asking me, well, they've stopped asking. They're all in their 30s now. They stop asking me, what is it? What kind of research do you do? I said, well, I design these linkages. You're still doing that? Is there anything, cool about it? I said, well, I don't know. What would you like it to do? Well, I'd like them to open a flower and close a flower. So that's where this problem came from. We did it with a 4-bar linkage. You would say, open a flower, close it. Why not just a hinge? Why not just a hinge? Well, it actually kind of looks better if it kind of moves away a little bit. Then you put a 4-bar in there, and you can actually get a nice 4-bar to do it. Part of the reason I'm showing you this is something that actually seems to be true, and again, this is just experiential, that our 4 bars provide the same movement, our 6 bars provide the same movement as our 4 bars, but they're packaged a little bit better. And I'm not quite sure whether that's because we specify the 3R chain in a way that we like, and in a way that we can't do for the 4R chain. So and I consider this part of the task, or part of the designer's choice, because we're having trouble actually characterizing what designers want out of a linkage. They know exactly what they want when they see it. Oh, I love that linkage. Oh, that stinks. What is it about this one that you like and about that one that you don't like? And I can't tell you that we have that figured out. But it's really true. They know it when they see it. Okay. I'm now going to talk about 8-bar linkages because this is where the combinatorics really start to show that you can't do this without a computer. All the stuff we did with 6 bars, we actually did on the computer, but we kind of did one at a time. You really have to have the computer start sorting things and doing the calculations for you to make an 8-bar work. So here we are. We're again the 5 task positions. There's actually 2 approaches that we have, and I don't think they're the only 2. It's just the 2 that we've been exploring. One is the 6R loop that's got 3 degrees of freedom. We now constrain the 6R loop by adding 2 RR chains. Okay, synthesis equations are exactly what I've shown you. It's very straightforward. But you can also do it with a 4R loop. Okay, 4R loop is sort of a redundant mechanism, so it adds a little bit of a twist in there when you try to do the inverse kinematics. And on top of that, you have to add 3 RR constraints, not just 2. But the result is a 8-bar linkage. This is the kind of thing you get. We considered this a success when we first did it. This problem actually came out of analyzing a sofa bed linkage. You know what I mean? The convertible sofa bed. I don't know if any of you, nowadays they've got all kinds of interesting new convertible sofas, but for many years they were always the same mechanism, and there's a mechanism that was invented like in the 30s. It's like really an old mechanism. It seems to be singular in some way. We really worked hard to try to design it. But what happens when you lift a sofa bed up is when you pull it up, it sort of goes away from you. You know, you lift it up and it pulls you forward. And then you pull it back and lay it down and then flip the bottom down. It's that moving away from you that actually they want to get rid of because it strains people's backs. Okay. So we spent a long time. It just seemed like it's not that much. You know what I mean? If you looked at the edge of the sofa bed, you know, the sofa bed comes up and it just pulls away by no more than 6 inches. You would think all we want to do is we just want to come up and just cut that in half, make it 2 or 3 inches. We couldn't do it. We worked on 4 bars, we worked on 6 bars. We finally got it to work. Whoops. Sorry, we finally got it to work with this 8-bar. Okay, you can't see it that well, but it does in fact come straight up. But of course that's not enough. The linkage cannot go through the floor, and it's got to go around this bar that goes across the back that sets up the whole thing. Well, not only that, the guy who wanted me to do this, I think we didn't get back to him for 3 years. I'm guessing I don't know, I haven't been able to find it since then. But he did inspire us. It was a very interesting problem. So this is where we are now. We're going to synthesize an RR constraint. So this is actually recent work that we've come back to. We're going to synthesize an RR constraint for a 6R loop, and then I'm also going to show you for the 4R chain. And the basic principle here is that we know the positions of these links. We know what we want these links to do because that's defined by the task. So the relative position of these links are all defined. So I write the kinematics equations. It gets me from this link to that link, just like what I've shown you in the notes. We wind up getting a set of equations. We get 5 equations and 5 unknowns, and we solve them directly. Okay. And then we consider all the different ways that you can do that. Now we did add a constraint. We said that we only want 2 pivots connected to ground, because those are 2 pivots we specify. And this gives the designer the choice. You get to choose how it's going to attach to ground. The designer even gets to choose how it's attached to the primary moving body. And the designer even gets the chance to choose where these elbows are. And as you would expect, everyone makes all of these links the same. So the only thing the system designs is really the constraints, the internal constraints between the links. Now there's no reason why we couldn't have a constraint that connected it to ground, but that could potentially put a pivot in a place that the designer didn't want. So we sort of removed that. But that's kind of a bias. It could be that there are linkages there that we're eliminating that we probably should consider. Yeah?
You're doing this and you're approaching what you would consider the ideal. Now what happens when you throw something like where in there?
In the design process, right, we start with trying to figure out what the customer wants. based on what we think the customer wants, we try to turn that into a set of characterizations of what a successful design would be. That always includes wear, maintainability, cost efficiency, all of that kind of stuff. The very next thing we do, and this is what it's important you understand, the very next thing we do is try to characterize how we want it to move. Now, quite often in many systems, how it moves is relatively straightforward, and that's a simple step, and we move on. It's a gear train, you know, it's a gear train, or it's a door that's swinging open. Okay, there's not a lot of analysis that needs to be done. What we're talking about here are systems where we cannot predict the constraints that are going to allow it to move the way we want it to move, right? So we're actually looking at solving that problem. Once we've solved that problem, we are nowhere near done, right? What we have to do now is we've got to size those parts. We've got to size the bearings. We've got to analyze the stresses. Once we're done with that, then we've got to do the dynamic analysis to try to predict performance over time. Do you know what I mean? And then you've got to take it, you know, see what you can do to manufacture it, what special materials might want to use. Do you know what I mean? So we're really at what I would say the inventive stage. We are right at the stage where we're sort of interacting with what we think might be a product the user wants. Does that make sense?
Yes.
So wear is absolutely critically important, but it has everything to do with loading, speed, you know, choice of material in terms of the links. All we're trying to do at this particular moment in time is figure out the dimensions.
Does that answer my next question? That is, back when you had your axles articulating, well, race cars do a lot of skidding around. Now you put friction on those wheels. What does that do to your design?
It puts incredible loads on it, right? Every one of these designs have incredible loading on it. And what you see here is planar loading with all the axles parallel. Most of the loading that damages these devices is out of plane. So you really have to, I mean, you can't design these things the way they're drawn. You've got to seriously consider the out-of-plane structure. You know, the web, you know, the flanges, the bearing supports. And these things have to move over each other, right? So that means that they are spread out even further in space. You've got to take that into account. How you package them in the, relative to each other in the plane is very important. And whether you actually package them in parallel. You might actually run two of them in parallel. So we're only, and the reason why I think this is important, this is nowhere, we're nowhere near a final product. We're just trying to figure out what would be a device that would work.
So we you design something that you think will work, put it out in the field, and let somebody break it?
I don't know any other way to do it. You've got to at some point, right? I mean, if you think you can design something without having it tested, you're in the wrong business, you know what I mean? Okay, so out of what that process does, let me just make sure. Okay, so this is where all the different choices you get if you're connecting the links independent of each other. If you rely on connecting the first link and the second link to the first link sequentially, you get these different choices. That turns out to be a total of 32. And it's kind of interesting if you compare it to the original list. This is the original list of 18 6-bar chains. This numbering means there's four binary and 4 ternary joints. So you can see the ternary joints here. This says there are 5 binary, 2 ternary, and 1 quaternary joint. So this is a quaternary joint. It's got 4 connections. Here there's 2 quaternaries, so they're here and here. And the colors show that we have designed these linkages, but we've got all of these that we haven't even touched. Now, does that mean they're any good? I don't know. Okay, but I did want to give you a little something to look at. So this is that same. This is that same. Let me see if I get it to go. This is that same 8-bar. That we were working on before, but it's now designed, it's sort of designed to be all on one plane so that we can actually, so that there's no overlap among any of the linkages, so that we can make it out of compliant joints. Rather than using hinges, we would use flexures. This is a 4-bar linkage that's been synthesized to drive this link in coordination with that link. And what you see is that we get a significant motion amplification, which is kind of, which they care about at the MEMS level stuff, I think. I've got a couple colleagues that work in that area, and they ask, and so these are sort of design explorations for them. All right, so now let's take the case of the 4R serial chain. So here's our 4R serial chain. Joint 1, joint 2, joint 3, joint 4. It's configured sort of like the, the 6R loop, just so that it's easy to visualize. And what you find is that, well, you can attach 3 RR chains independently, and you get this case. You can attach 2 of them independently and add the third to one of the 2. Okay, so that's what you're seeing here. And so you get these different cases. And surprisingly, there's like even more where you attach, 2 links independently, and you now attach one of the links to the previous ones. And it goes on even more. All right? So, yeah.
So the scripting we showed in the previous slide using 8 bars, right?
Yeah.
Could that be achieved using 6 bars as well, or was there a reason we chose the 8 bars?
We have done, this is this rectilinear motion concept, right? We have done a lot of rectilinear motion things where this link moves in a straight line. We can't get the level of precision in the motion of this link in a straight line for any other linkage than the 8 bar. We haven't, so you're going to see more. I'm going to show you more because we do a lot of 8 bar rectilinear motion just because it's a good test. So the reason why we stacked it, what makes it stackable is the fact that this moves in a straight line and it doesn't move up and down. And so that's why we stick with the 8 bar. Okay. All right, so lots of 8 bars, lots of 8 bars. Okay. All right, so this is an illustration of what we're able to do now. So this is the 4R chain moving in a straight line. That's how we do it. Okay, this is the 4R linkage moving in a straight line with its constraints. And that's just one design. Here's another design. Again, moving in a straight line with a set of constraints. Okay, here's another one. And we get a lot of these now. There's another one. And here's another one. Now, my question to you is, if you had to choose between those 5 chains, well, first of all, knowing that they're skeletons and that you would have to configure them differently. In your own mind, did you have one that you like better than the others? Do you know what I mean? And that's an important question, and we haven't gotten there yet. The way we sort them out is the ratio of the longest link to the shortest link. So we take that number, and we try to keep that number. We just go from smallest to largest in terms of the ratio of the largest to smallest link. We have actually looked at other ways of doing it, such as mapping out the space that the linkage sweeps through, measuring the area of the linkage in one position versus the area of the linkage of the other, adding up the overall lengths of the links, trying to measure maybe something about the magnitude of the material involved. We've tried to do all of these. Our general experience is that people seem to like, or even, and when I say people, I mean us, seem to like our links to be relatively equally proportioned. A real long link and a real small link, people kind of seems to bother us for no practical reason. A very short link is really good sometimes. Anyway, this is now what we find in terms of our coverage with the 4R chain. We can design all of these topologies except this one. All right. Okay. All right. So that's, how am I doing on time? Should I just quit while I'm ahead? How much time do I have?
When we were supposed to stop.
I think it's 2:30 when I'm supposed to stop. You want me to just keep on going? I can. Huh?
If this is a good stopping point, we can move.
No, it's not a good topic. No. Are you guys really uncomfortable?
Yeah.
Okay, let me just go after it. I'm 2/3 of the way done through the talk. The talk will be over in a half hour, or less than a half hour. In fact, it'll be over quicker than that, because this is crazy, what we're about to see. Okay. All right. the basic synthesis there, I'm going, by the way, I'll just be honest with you, we're going back to 6 bars, so don't misunderstand me. When I say we're just going to get crazy, it's got not because I'm going to 10 bars, 20 bars, 30 bars, whereas that's where I would like to be going, but what we're really going to be doing is going back to 6 bars. The one thing I'd like you to understand is our synthesis theory in every situation up to this point has been built on solving 5 quadratic equations. Right? Because that's what the constraint equation is when you apply it 5 times for 5 task positions. So you're solving a rather, well, I mean, let's not downplay it. It's a rather complicated set of equations, and it takes a very significant subroutine to solve those equations. It runs fast. It's it uses standard polynomial elimination techniques, but it's fast. Okay, we're solving a system of equations that has 4, at most 4 roots, but you wind up having to admit the fact that this is a degree 32 set of polynomials. All right, with that as an introduction, this is what we're looking at. 6-bar linkage synthesis, Watt 1, Watt 2, Stevenson 1, Stevenson 2, Stevenson 3. We're going to talk about the standard synthesis is function generators, motion generators, path generators. All right. Again, this is what's been handed down to us, and I sort of blame myself. I haven't really thought about the task that much. Essentially, people who work in the area or worked in this area before me and before you said that the tasks kind of break down into these 3 general areas. Function generation, I coordinate an input angle to an output angle. It's the trash can problem. I step on the paddle of the trash can and the lid pops up. Pure function generator. Motion generator is what we've been talking about. I've got a body that's moving along a task, and I want to design it, I want to design the linkage that guides it through all of those positions. Path generation is a special case of that. It says, I don't care how the body rotates, I just want a point on the coupler to trace a specific path. Okay, I just want it. Now that problem in itself is kind of interesting. The linkage that will trace a particular curve. I don't know if any of you guys have friends who are in the computer science area, but that's been an area of really a lot of energy over the past 15 years. Are you guys familiar with what I'm talking about? They talk about designing Kemp linkages. No? You guys haven't heard about this? Okay. Well, good. I'll tell you. It comes from a theory. It comes from a theorem that Kemp formulated and attempted to prove, which says that a linkage can be designed that will trace any algebraic curve. In other words, any algebraic curve that you may create in the plane, there is a linkage that can be designed that will trace that curve. And the way he proved it was actually kind of interesting. If you look at it, you get the polynomial, you get the general construction of the polynomial equation. He created a multiplier linkage, a scaling linkage, and an adding linkage. And so what he could do is whatever the parameter was, he could scale it, and he could multiply it, and he could add it. So he could take whatever these parameters were and add up all of these linkages, and then he used a straight line linkage, postulated linkage, to sort of project it so that he got whatever the curve is that he prescribed. That was exactly what he proposed. Around the turn of the century, around 1999, 2000, a couple of geometers from University of Davis, I think, sort of found that result, and they said, well, that's kind of interesting. I wonder if it's true. And they wound up proving a very general version of that. And in fact, it's been re-studied and reproven in broader and broader form, which basically says that there is an articulated device, a planar mechanism that will generate any semi-algebraic curve that you want. In other words, they can handle corners, so they get piecewise algebraic curve. And they phrase it this way. They say, so there is a linkage that will sign your name, all right? That it can be constructed in theory. The computer scientists have gone crazy with this, and it's really fun because I mean, there's MS theses on this, there's software on it, and there's some interesting papers on it that show you these mechanisms, and they are just ridiculously complicated. And it's kind of from, which may be a bad thing. That might say more about me than it says. I actually enjoy the fact that they're so complicated. But what?
Autopolynomial still has a fork on.
Oh, well, I was going to get to that. That was a slide I was going to put in here, but I'm going to save it for my proposal. So any of you are on the review panels, be ready for this. I'll give it away. I think it was Saxena in India, one of our colleagues, who wrote a nice paper. It was a popular article. He wrote a nice popular article about this theory. It was something he wanted. I don't know who he wrote it for, but I stumbled on it. And what he shows very nicely is how you design one of these Kemp mechanisms for a relatively simple equation, a quadratic equation. And when he's done, he sort of laid it out very carefully, and you can sort of see it. It's got like 51 joints and like 100 plus links, or 70 plus links and 100 something. And then you just have to open Artabalevsky's book, and he's got how to draw a general conic with a 6-bar linkage, right? So I mean, these things are kind of setting the background for the kind of work that we're looking at here. And the reason why I'm bringing this up is because these problems, when you set them out in their most general form and you don't simplify them like we're doing with specifying a good chunk of the design with the 3R chain, have some stunning complexity. Okay, here's the path synthesis for, you can get 15, I'm going to show you the equations, but I'm going to go through it relatively quickly, but I'll just point out to this. The synthesis, the general path synthesis problem for a Watt1 linkage, which means it's out on this link somewhere, I'm tracing a path, has a maximum of 15 positions. In the plane, for the 4-bar linkage, it's 9. And the degree of the polynomial system, I'll grant you it's not the most optimal polynomial system. Can anybody read that? 10 to the 46th. Now, I actually checked. It turns out that there's 10 to the 54 molecules in the Earth. Okay, so it's not the entire Earth, but it's a good chunk. I mean, if we use the Earth as the computer storage for all of these roots of this polynomial system, we would use a big chunk of, a big chunk of the Earth. It's not a big chunk. It's like 46 from 54 is like 10 to the 8th. So it's only 1 billionth that the Earth would be used for the storage of all this stuff. Anyway, but the problems actually get pretty large. Some of them are really simple because these things are they reduce down to designing a 4-bar linkage in some way. But some of them get to be really complex quickly. So this is one that we've just been able to get some results for, and I'm going to show you that here. We've got what stuff that's in red is the pieces that we've been able to get. We've been able to formulate the equations, but they're so big we can't solve them. They're so big that we can't solve them with the computing resources we have. We use Bertini and the HPC at UCI. We haven't really turned them loose. I probably would like to, we sort of want to verify our formulations and stuff, but we want to turn them loose on a supercomputer at some point, but we haven't quite gotten there. So the path synthesis problems just seem crazy. This again reduces to the same problem as the 4-bar linkage. This is the one we've been able to do. We've been able to do 8 positions for the Stevenson 2 and 8 positions for the Stevenson 3 and 6 positions for the Watt 1. And I'm going to show you those results. Okay, and probably the main point that I'd like to make is that the formulation of these equations is just old school loop equations. And it's old school kinematics equations for robots. All of this stuff is the same. There is no, well, my Dennett-Hardenberg formulation is better than your product of exponentials formulation. I mean, get rid of that thinking. Oh, my standard form equations is better than your algebraic equations. No, they all come from the same basic geometry, which is, closing the loops on that device. So we have these loop equations. The only thing I'll point out here is that we use this trick that was introduced by Wampler, and this is something I would have never have known to do. You formulate the equations in their complex form and in their complex conjugate form. And then what you do is you treat their complex conjugate and their regular form as independent variables and introduce, the fact that they're complex conjugates, which means if you multiply them against each other, they have to have a particular value. You use that as a constraint equation. That turns out to give you a set of equations that you can manage in these polynomial homotopy solvers very nicely. So that's a nice trick, and Wampler is the one that pointed that out to us. So we get these loop equations. They partition in a particular way. We can get, for example, in this case, we get 70 equations and 70 unknowns with degree 21. The methodology of getting us there is straightforward. It boils down to now solving these things. Okay, Mark actually solved this for a rather interesting problem. This is a rehabilitation device where what they're trying to do is control the spring rate. They have this mechanism sprung, and they wanted a mechanism that transformed it into a particular type of spring. And it's a very counterintuitive spring. It's a spring that's soft when it's near the neutral position. No, it's soft when it's away from the neutral position and really stiff near the neutral position. Yeah, and I'm not quite, well, all right. Have I got it completely wrong, Mark?
Well, it's at like an unstable equilibrium. And it's a reverse spring. So the more you move,
the more you move it,
the more force. So the further
the
you
less
move,
force, right? The closer you are to neutral position, the more force.
Yeah.
And the idea is that it's intended to help stroke patients with tremors. What do they call it?
They have a spastic wrist.
They have a spastic wrist, and it helps stabilize their wrist.
Yeah, they'll have additional stiffness after they have a stroke in the motion of their wrist from moving it from one.
So they don't need the extra stiffness out here. They have trouble in here. That's where they need the stiffness. I don't know.
Well, it's actually near the exterior.
Okay.
Yeah, that's where they have additional stiffness,
Right,
so
so
that cancels it out.
That cancels it out. Okay. And it turns out it works really well. Well, we haven't heard. He's still working on the latest device, right?
Yeah, they're adding adjustments to it now, but they've tested it somewhat.
Same set of equations. Same set of equations, adapted just a little bit differently for the fact that you're moving a body. Loop equations, conjugate loop equations. Organized, same sets of variables, same sets of constraints, 8 task positions. In this case, again, 7 equations, 7 unknowns, degree 10 to the 21, which is, when we talk to these guys who are doing who develop Bertini and do polynomial homotopy solvers, they like us. I think they like us because they spend a lot of time talking to us. But when we tell them that we want to solve polynomial systems of degree 10 to the 21, basically they go, why? And I think that's probably a fair question. Okay, so here's an example. This is a solution which is, again, Mark's working on this one. This is what you're presenting, right? Kostub, by the way, I'm stealing their thunder, and I'm going to give them credit. Kostub is presenting the 8-bar mechanism stuff at this conference, and Mark is presenting this 6-bar synthesis at the conference. Let me just show you his animation. So this is a suspension that's now not your typical double A-arm independent suspension. It is a 6-bar linkage. Now the question is, why would anybody do that? And that's it's a really good question. I don't know whether you can see it, but what it does is it allows the suspension to lean into the turn. Each of the individual tires move up and down like it would if it went over the bump. But now, Mark, which way is Which way do we want to tell them that we're driving forward?
So to the left of the screen would be rear. To the right of the screen.
So
would
this
be
is the rear.
Mhm.
So when this would it be turning right? Let me do it. Let me get back to the beginning. So here it's turning right. So instead of rolling this, when you make a right turn, your center of gravity, by definition, causes the car to roll away from the turn. By having your suspension lower the right side, you use the weight of the car to counteract that centrifugal force. That's the idea. We have yet to see it actually work. Okay, these are really recent results. This is using the same sort of theory to try to design a very high extension suspension. So this is the, for a Baja going over boulders and stuff like that. And then, when you design a high extension suspension like that, you often give up roll. So one of the things he's trying to do is show that you actually keep, you don't get the reverse roll that he has in the other design, but at least it does control the roll when the tires go over bumps. Okay, so what that was function generation, this was motion generation, this is now path generation, and this is where things get really out of hand. Same set of equations, loop equations. Again, same, things all sort of work out. In this particular case, he can now do 15 task positions, so he has 154 quadratic equations and 154 unknowns. Total degree 2 to the 154, otherwise known as 10 to the 46th. This is as far as we've got. All he did was take a linkage that he knew the answer to and was able to verify that his synthesis equations work.
Well, that's a new design too. So I knew that one had a solution, but that's a different solution than.
Oh, so this is you knew that one. So this was a solution that came out of your calculation.
Yeah, from just brute forcing it and trying to find something.
So this is the last time you're going to let me give your talk for you. All right. This is probably the last time I can claim to have helped them on their work. Okay, so this is it. This is the end of my talk. Where can I get more information? Where can you get more information? I've got, first of all, Mark has got a nice paper that was published in the Journal of Mechanisms Robotics, and also his recent paper at the Advances in Robot Kinematics. There's a bunch of stuff that I've got out there. A lot of this is described in the 21st Century Kinematics book, which I have copies of. I'm willing to mail it to you if you want it. I have a online, I've taken some of my old books and configured them into e-books that you can download online. This is one, I created this one for myself, and it's basically just a very simple step-by-step approach through the sort of basic polynomial theory as it applies to a couple of useful kinematics problems. The analysis of a planar platform and the synthesis of 4-bar linkage and the SS chain. Mechanism generator is out there. You guys have any interest in it, just let me know. And then this is what's happening from my students here at the conference. Okay, Brandon's been talking about the work he's trying to do. It's a lot of theoretical work in the beginning of trying to understand exoskeletons. This is Mark's vehicle suspension design, Kostub and his 8-bar linkage stuff. So I've stolen his thunder on that, but I'd like you guys to go see that. And then Brian has sort of been crucial to this. We can't design these linkages and be sure that they're going to work without also analyzing them, right? But we need an analysis routine that's very general, that will take whatever graph that we have of this mechanism, turn it into equations, solve those equations, and give us the answers back in a reliable way for literally hundreds of cases. And that's what he's done with his 8-bar linkage synthesis routine. Turns out it's been very helpful. We couldn't do this without it. Because the main problem is you can't do the synthesis by itself. Your synthesis routines give you linkages that don't work. So once you've done the synthesis, you immediately have to do the analysis in order to verify that they work. And what we're seeing is, 1 out of 100. So we'll design roughly 100 and then get one that works. As we start to get more and more complicated systems, it's like 1 in 1,000, then 1 in 10,000. So it really relies on a computer, to sort of really sort through these things. We should find ways to be, at some point we'll try to find ways to be more efficient. At the moment, we're just thrilled that we're finding these linkages. We're finding very nice designs. Anyway, that's my presentation. That's all I'm trying to do here is say thank you. Thank you very much. It's getting warm in here, but do you have any questions? Well, I'll answer the questions. Yes?
It looks to me like you're up against computers doing the same thing. Who's winning?
No, I misportrayed it. This would not be possible without having the computers sort through this stuff.
No, that's not what I'm talking about. I'm talking about, I attended the American Welding Conference, I don't know, 10 years ago,
Yeah.
I guess already. And they put string of lights around a Harley Davidson, and then the robot just traced.
Oh, you're talking about, yeah. So, no, that's a good question. Right, so, any of the things that I've done here, you can program a robot to do, right? That's really the point. So why did I go to the trouble, all of this trouble, to design a 6-bar linkage when I could just put a robot in there to do it? Correct?
Yeah.
Well, okay, let's just look at the cases that I showed you. Number one was an exercise machine for a hand of a stroke victim. Okay. I mean, I probably could put a robot in there that had the power. I mean, this person has a lot of power. Even though they're a stroke victim, they've got a lot of power. So you need a rather strong motor under computer control that person's holding on to. Yeah.
And then a comment on that is they had that set up.
Yeah.
And the idea behind this project was to remove that specifically so we could have a passive version.
Right.
Because also the passive version could be extended and implemented on something besides just this benchtop, testing machine to maybe like a device that you just put on and it's sprung and you can wear it for everyday use.
That's the idea. You can be smaller, more compact, then you can make a strong row. So you can do with springs and linkages what you can't do with servo motors. A servo motor is basically a spring, a controlled spring, all right? And so if we can actually use a real spring, we might be able to do it cheaper and easier. Now look at the 6-bar suspension. Certainly we could put a 3R chain in there and try to control the arms on that. And I think that the military tries to do that on some of their advanced vehicles, to actually have sort of robotic controlled legs. But that's really, I mean, that's a very power intensive application. I'm not sure they've been that successful. Okay. You can actually see it with these running robots they have, such as the Big Dog. They're like running along. Now that Big Dog's got to have the equivalent of suspension, which is the 4 legs carrying it relative to the ground. And that's, it's running on a lot of power just to keep its suspension up. So having a passive system that does the job, I think is very important. Okay, now for tracing a curve in space, that's one of the things that robots do really well, right? I mean, that's what, as you say, a welding robot can just do it without any difficulty at all. So the competition there is, I don't know, I'm not quite sure how we're going to do in that one. But if we get a solution, we just got to turn our computers loose on that solution. Maybe we can do something useful. Any more questions? Yeah.
The link you showed
Which one?
the initial one.
The very first one. All the way up here?
Yeah. Yeah, this one.
Okay.
No, second. Okay, go forward.
Sorry.
The one that we have designed combined.
this, I mean, this 8-bar.
Yeah.
Okay, it just reminded me how a combination of Scott-Russell mechanical.
Yeah.
Can you recall the Scott-Russell
Yeah.
mechanical?
Uh-huh.
Okay, what is the, I was wondering